Hi everyone. In this video, we will begin our discussion of our final unit, which covers sequences and series of functions. I want to take a slightly different approach than the approach the book takes, which is that I want to begin our discussion by simply examining a number of examples of sequences of functions to help build our intuition for what sequences of functions can look like and what types of different behaviors we might want to be able to rigorously define and what types of implications we may see for those observations. So to begin, let's first begin by simply defining a sequence and a series of functions. So imagine we have a set D. That set D is going to be our common domain. And we have a collection of functions. So for every natural number n, we have a function f sub n, which maps from D into the real numbers. So then that set of functions, that collection of functions, forms a sequence of functions. So f sub 1 is simply the first function in that sequence, f sub 2 is the second function, so on and so on. And if I take the terms in that sequence and sum them together in that order that's given by the sequence, then we formed a series of functions. So you may see that in a lot of ways this is virtually identical to our definition for a sequence of real numbers. There we defined a sequence of real numbers as a function A, which maps from the natural numbers into R. Now, it's slightly harder to write the definition of a sequence of functions in this way, in part because it's not clear what our output set should be. It should be like the set of all possible functions. It's just a little harder to express in that same manner. So we do sort of leave this slightly more general definition. Okay, or I shouldn't say more general, but just maybe less rigorous definition. But it is indeed exactly how we want to think of sequences and series of functions. So as I said, we're going to look at three examples in this video. So the first example I want to look at is simply f sub n of x is equal to x to the n on the set 0, 1. Okay, so again, just to go back and think about exactly what that definition is saying, right? I have a first function, f sub 1 of x, and this expression is telling me that that function is just defined to be x to the first, or just x. I have a second function, f sub 2 of x, and it is simply x squared, okay? And so you can see, right, how this is going. And then in general, right, the nth term, f sub n of x, is just x to the n. So again, we can express this in a number of different ways. We could write it in this form. So x squared, x cubed, x to the fourth, so on and so on, right? But we're just representing here, I'm thinking of each of these as a different function. So this is f of x is equal to x, f of x is equal to x squared, f of x is equal to x cubed, and that forms a sequence of functions. So if we want to consider these functions on the common domain 0, 1, another way we can think about these is simply by plotting them. So if I draw some axes over here, I could come and I could begin plotting this sequence of functions. So the first function is simply going to be the function. And again, we're only working on the interval 0, 1. My first function would be this. My second function would be like an x squared. My third function would be like an x cubed. So on and so on and so on. Okay, so I can begin to express and represent this sequence of functions in a number of different ways, right? I can simply write out the terms and arrange those in different ways. Or in this case, right, I can sort of visually or graphically think about what does this sequence of functions look like. Now, as soon as I have some sequence of functions, or a sequence of anything for that matter, a question I might start asking is, does this sequence approach something? Where approach is not particularly well defined. So if you think back to sequences of real numbers, right, we needed to formally define what we meant by saying a sequence approached some value, right? And we did that via defining the limit. Okay? Now, if you think about a limit of a sequence of real numbers, right, that limit value was another real number, right? So sequences of real numbers could approach real numbers. We might wonder, does it make any sense to think about a sequence of functions approaching some other function? So to help us do that, in each of the examples we look at today, I'm actually going to pull up Desmos, and let's let Desmos show us visually a little more of what's going on. Instead of me trying to continue to draw these pictures, which I can do for a few cases, but let's actually use some computational tools to help us look at, what's happening to this function as n gets very large. So before we switch over, I encourage you to spend some time thinking about what you think this sequence of functions will look like as n gets larger and larger. Now let's switch over to Desmos to take a look. Great. Now here in Desmos, you can see what I have plotted here right now is f1. It's just y is equal to x, and we're working on the interval from 0 all the way up to 1. Okay. And so you can see, right, this is the point right up here, 1, 1. And now we want to look at what happens as n gets large. So you can see here, I have a little slider for n, so I'm just going to turn that up. And so let's see what happens as n gets larger and larger and larger and larger. Okay, so we can see what's happening, right? For many of these points, right, for many of the x values, that seems like the function is being sort of just pulled down, right? It's almost like I'm grabbing a hold of this and just pulling it down. But the function's also sort of stuck up here at 1. And if we think about what's going on here, right, if I think about my looking at just this point, so this is when x is equal to 1, what I have is that f sub n of 1, right, that's just going to be 1 to the n, which is always going to be 1. So every one of these functions is stuck up here at 1, right? But if I think about any other point on this graph, so let's say I come here and I'm somewhere around, let's see, what am I here at about a half here. So if I think about 1/2, if I look at f sub n of 1/2, that's going to be 1/2 to the n, and that's going to go to 0, right? So these points are being dragged down to 0, but this point at 1 is just sort of stuck. But for every other point, if I were to pick 0.99, right? If I were to pick anything smaller than 1 and raise it to the nth power, those points are all being dragged down. So what I get the sense is happening is that everything is being dragged down to 0 except for this point right up here at 1. And so indeed, right, we could imagine that our sequence of functions is converging to this, and it's a little hard to see. Let me turn up let me increase the thickness of this line a bit, right? Maybe even a little more than that. All right, if you look down here, it's like this function is 0 all along the x, right, all along the x-axis up until we get to 1, but at 1, right, our function value is 1. Okay, it's like I'm converging to the function that's 0 from x is equal to 0 up to 1, not including 1, and then at 1 has the value 1. So now if I, again, increase that n, it feels like we're sort of approaching that function. Okay, now this is only taking n up to 100. Obviously, you see maybe, which feels like a little error down in here, but if we kept cranking that up, right, we would see even those points start to come down there. Okay, so this notion, this idea that we could determine what happens to the sequence of functions by sort of fixing any particular x value and looking at what is happening there, that's going to lead us to something that eventually we are going to call pointwise convergence. We don't need to worry about the formal definition right this second. Again, we're still just building intuition, but that is worth noting. So let's switch back from Desmos now to make a few concluding remarks about this example before we switch to our next. So we observed here that this sequence of functions appears to be converging or approaching. Oh, I left one of the p's out there. This appears to be approaching the function, which we'll call g of x, which was 0 when x was between 0 and 1, including 0 but not 1, and 1 when x is equal to 1. Now notice that if we can make this notion of convergence rigorous, right, if we can formally define this and prove this, then we do have sort of a weird thing going on, which is that if I look at each of these functions, this is a really nice function, right? Well-behaved, continuous, differentiable, all the nice things, right? There's a very nice function. Each of these functions for any fixed n is a very nice function. However, what we're seeing is that what it is approaching is actually a discontinuous function. And of course, since it's discontinuous, it therefore fails to be differentiable. So again, what we see here is that we have some type of convergence. It appears that that convergence doesn't preserve nice properties that we might care about preserving. For example, continuity. It appears that under this definition of convergence, a sequence of continuous functions will not necessarily have a limit that is continuous. So even though we can find the limit, it's sort of not of the same type as the sequence of functions. Right? Now, this is maybe, we can look at this two ways. Either this is just a fact we have to deal with, or maybe there are ways of modifying later our notion of convergence to make it so that we do get a continuous limit. Now, for our second example, okay, I want to take something that's maybe at first a little bit harder to make sense of. So I want you to consider now the following sequence of functions, each of which is piecewise defined. So I'm defining this function for each natural number n, and I'm defining it on the interval 0 to 1. Okay. So we have f sub n of x is equal to 2n squared x if x is between 0 and 1 over 2n. It's equal to 2n times 1 minus nx when x is between 1 over 2n and 1 over n. And it's defined to be 0 when 1 over n is less than x is less than or equal to 1. Okay. So what I want to encourage you to do is to pause this video and try to do two things. Plot f sub 1 of x by hand, and plot f sub 2 of x, right? So pause the video, just see if you can, by hand, plot these for these specific values, right? Notice what I'm doing is I'm giving a specific value of n. So you can substitute in the values of n and see if you can plot these. Once you're able to do that, you may then ask yourself if you can describe in general what f sub n of x is doing. Often it's helpful to have sort of a few smaller cases understood and then see if you can describe what's going on more generally. So again, I encourage you to pause the video here, see what you can figure out, and then come back and we'll discuss these all together using Desmos. Now, before we switch over to Desmos, let's make a couple of observations here, right? The first is that for any fixed value of n, this first part is a linear function, right, of x, right? So for a fixed value of n, this is linear in x. When x is equal to 0, this has the value 0. And when x is equal to 1 over 2n, so I plug in 1 over 2n here, I just get n. So if I sort of think about graphing this, right, I know that on the interval from 0 to 1 over 2n, I have a line. It starts at 0 and it goes up to a height of n. Now, looking at the second part, if I observe this, if n is fixed, for a fixed value of n, this is again linear in x. Okay. I know that if I plug in 1 over 2 to the n, it might, for x, so I plug in 1 over 2 to the n for x, might take a little bit of algebra here, but I'll notice that what I actually get is n. Okay. So this is, again, a function which at 1 over 2 to the n has the value n. So that's nice. That matches up and makes these continuous at 1 over 2 to the n. And at 1 over n, if I plug that in, it has the value 0. Okay. And now for everything bigger than 1 over n up to 1, my function is simply 0. Okay. So what I get is that for any fixed value of n, this function gives me a triangle, right, with the vertices 0, 0, 1 over 2n, comma n, 1 over n, comma 0, and then everything else is simply 0. So let's flip over to Desmos now so we can really get some perspective on what these look like as n varies. All right, so here we have plotted f sub 1. So again, we now understand this should be a triangle. It starts at 0, 0. It goes up to the value here. It's just behind my laptop screen now. It goes up here to the value, the height 1 at 1 over 2n, or 1/2. And then it goes back down to 0 at 1. Here, there's nothing between 1 over n, which is 1, and 1, so it's just back down at 0. Okay. But now if I increase my value of n, so let's take n up 1. Okay. Now I have a triangle that has height 2 at 1/4. Okay. And so it goes 0, 0, 1/4, comma 2. And then down here at the bottom, we're at 1/2, 0. Okay. And so now what you notice is as I increase this every time, what happens? The height of my triangle goes up 1, and the base is it goes to 1 over n, right? So this has base 1/3 and height 3. We go up to 4, base 1/4 and height 4, and so on and so on and so on. And notice that all the rest of these points are just becoming 0, right? All the rest of these are now just falling into that category where x is between 1 over n and 1. Okay, so as I keep going, and eventually sort of the peaks of these are going to start to run off the screen, but you could sort of ask yourself, well, what is this converging to? So again, if I back it up, and I can just let it play here for a second. And you can see those. So these sometimes call these marching triangles. Right, so these triangles are sort of marching towards the origin, and they're getting taller and taller and taller as you go. Now, notice, right, a lot of these points over here, right, they're just sort of quickly going to 0, right? Because eventually what happens is they get caught up in that tail end of the piecewise function, right? And so they're all going to 0. Now, seemingly, though, things are getting crunched near the origin. And so the question is sort of, well, what is happening at all of those points? Well, if I picked any point, so say I come over here and pick some point down here, whatever it is, but let's just call it x, where x is bigger than 0 and less than or equal to 1. Well, if x is between 0 and 1 and it's not equal to 0, then this implies that there exists a capital N, a natural number, such that 1 over n is strictly less than x for all little n greater than capital N, right? So eventually I can go out far enough so that in the natural number, so that 1 over any natural number is less than any positive value of x that I've fixed, right? So if my number x is 1/10, right, then I need to go out past 10, and then every other value 1 over n will be less than that. But I can do this even if it's not 1 over something, right? If x was, pi to the 5th over 7,000, right, there would still be some natural number such that eventually 1 over n was less than x for all little n greater than that natural number. Well, in that case, what that tells us is that eventually f sub n of that particular x value. So I'm still just looking at x values that satisfy this property. But then eventually f sub n of x will be equal to 0 for all little n greater than that capital N, which tells us that the limit as n goes to infinity of f sub n of that fixed x value will be equal to 0, right? If eventually, for a fixed x value, this is just a sequence of real numbers, right? And so if I plugged in a particular x, right? So for a fixed x value, this is a sequence of real numbers. I know that for any x values in here, eventually that sequence is always just equal to 0. So that means the limit must be 0. So that means for all of these x values, if I'm going to have some sort of limit function, right, then I guess the limit function, let's call it g of x. Well, whatever it is, it better be 0, certainly better be 0 for 0 is less than or equal to x, or sorry, 0 is less than x is less than or equal to 1. But then that still brings up what happens when x is equal to 0. Well, if we come back to our function, right, when x is equal to 0, when x is equal to 0, and I've got these sort of three pieces written here, but the x is equal to 0 piece goes here, right? Then f sub n of 0 is always 0, right? You plug in 0 to this first expression here. For any n, you're going to get 0. That means obviously the limit as n goes to infinity of f sub n of 0 has to be equal to 0. And so it feels like this should also be 0 when x is equal to 0. It feels like the limit function should just be the constant function 0. Okay. And in fact, and again, we have some rigorous defining to do, but in fact, this is exactly the right answer, right? The limit of this function is 0. Now, I bring up this example because I think it certainly made me feel uneasy the first few times I saw it, because it feels like all of these triangles, they're sort of stacking up, right? And they're getting higher and higher and higher. If I go back to the sort of animation here, and let's stop that for a second and just see if we can just bring back the slider. Oops. We'll add a slider. There we go. Okay. So if I'm here with this slider, oops. All right. So if I adjust this, right, it feels like these are all like, how can these be going to 0, right? Because it feels like these larger and larger triangles, like the function values must be getting larger. The problem is that the places where it's getting larger are disappearing, right? And so in fact, in the limit, this is just limiting to the 0 function. Now, it does bring up another interesting phenomenon though, right? If I were to look at the integral from 0 to 1 of each of the f sub n's of x. If you remember, each of these was a triangle. It was a triangle with base 1 over n and height n. So the area of each of these triangles was just 1/2 base, which was 1 over n, times height, which was just n. Each of these triangles has area 1/2, and therefore the integral of each of these functions, right, is just 1/2, right? Outside the triangle, the function is just 0, right? So that's not going to contribute anything. So really all I need to look at is the area of this triangle, which is always 1/2. But if we look at the limit as n goes to infinity of f sub n of x, right? We've already seen that's this function which is just 0, and obviously the integral from 0 to 1 of 0 dx is just 0. So I think what feels strange here is that you have a sequence of functions, and each function has integral 1/2, but the limit function doesn't have integral 1/2, it has limit 0. Now, if each of these were, say, if the integral of each of them was like 1 over n, so the areas were getting smaller and smaller and smaller, you'd probably go, okay, this is sort of like the air leaking out of the balloon, right? But in a way, what you feel like is happening here is almost like a balloon popping, right? There's a fixed volume, fixed volume, fixed volume, fixed volume, fixed volume, and then all of a sudden everything's gone. Okay, which I think is what leads this to be a little bit surprising. Now, this is a really good sequence of functions for generating certain types of counterexamples, and we will make use of it and look at it more as we go on. Now, I will note, though, in this case, right, we have a sequence of functions, each of which is continuous, and its limit is also continuous. So again, we're seeing there's this sort of weird mishmash of some things are preserved, some aren't. I don't know if these things are always preserved or just in this particular case, right? But there seem to be weird things going on about what properties are or are not preserved when we look at these sequences of functions converging to something. Now let's switch back over to look at our final example. Now, in this final example, we're actually going to look at a sequence of partial sums, right? So this is, again, a sequence of functions, right? But it's a sequence of partial sums from a series of functions. So you can imagine we have the infinite series, k equals 0 to infinity, minus 1 to the k times k plus 1 times x to the k. And I want to take its sequence of partial sums, right? So I just replace this infinity with an n and look at what happens as n gets larger and larger and larger. So if we just start writing out some terms over here, when k is equal to 0, I will just get 1. When k is equal to 2, I'll get a minus 2x. When k is equal to 3, I'll get a plus 3x squared. And you can start to see what's going on here. Oops, should be an x cubed plus 5x to the fourth minus, okay, so on and so on and so on. So what's happening here is our signs are alternating, positive, negative. Coefficient otherwise is going up by 1 in absolute value each time. And the power on x is always 1 less than the coefficient. So here we have a coefficient of 2, power of 1, coefficient of 3, power of 2, coefficient of 4, power of 3, so on and so on. Okay. It's sort of an interesting historical note. Mathematicians, certainly as far back, probably even further back than Euler, have been looking at these types of infinite series. And this led to some interesting things. So, for example, Euler had some inclination that this infinite series was related to this function. Euler had some inclination that this series was related to this function, okay, which led him to have some sort of conflicting beliefs about, so if you take, for example, and substitute in x is equal to 1, on this side, that would give you 1/4. And if you look at the terms of this, which again, I've pretty much expanded out here, obviously this finite sum would stop at minus 1 to the n, k plus 1, x to the n. But if we keep going and going, we get this infinite sum. And if you write out what happens when you plug in x is equal to 1 here, you get 1 minus 2 plus 3 minus 4 plus 5 minus 6, so on and so on. So he seemed to have some notion that this series should actually diverge. At the same time, like these were equal. And really the problem was he was trying to reconcile what was going on with this series of real numbers, which he seemed to clearly have some notion was diverging, with the fact that it seemed like this sequence of functions was converging. Now, the issue, and I've played a little fast and loose with it here, is that we haven't said on what interval we're looking at this function. So the problem is that this sequence of functions does not converge to this function when 1 is in your domain. Okay. However, if you have say a smaller domain that doesn't include 1, then you might have a chance of this sequence of functions converging. So again, let's look at what's going on here. Again, we can look at what these terms are of this series. Okay, but let's use Desmos to help us, get some sense of what's going on and what sort of things we might want to prove. in subsequent videos. So I have plotted here in this blue color, this would be f sub 1. So f sub 1 is actually just going to be, because we're starting this at k is equal to 0. So this would be 0 and 1, right? So I would get, this is 1 minus 2x. That's what this function plotted down here is, right? And then if I add the next term, right, I'll get a plus 3x squared. If I increase this m, just fix this. I just increase this by 1. All right, there's that function. And I can keep increasing this, okay? Now notice as I do this, right, and this isn't surprising, right? See this tail on the end over here is sort of wildly oscillating back and forth, right? As I increase each time, right? And that's sort of to be expected, because if you think about it, each time I'm adding on a different highest power, so anytime I'm adding on an even power, I have a positive coefficient, right? But anytime I add on an odd power, so if I go to add on the next odd power, I have a negative coefficient. So that's going to flip this down, because basically you can think of this as like a minus x cubed. So up at negative infinity, as x goes to negative infinity, it goes to positive infinity. As x goes to positive infinity, the function goes to negative infinity. Then when I add on an even power of x, right, I'm adding on a positive term, and so now for even powers, it goes up on this end, still up on this end as well, right? So I'm getting this sort of wild oscillation back and forth, right? And notice that, like, if I back up here, it looks like for a while, like, things are sort of going okay. And if you look at sort of the x values, like, it's not changing, it's still changing a little bit, say at 0.6, right? So if you look at 0.6, like, my function values are still changing a little bit, but if I go a little further out, now it's not moving very much at all at 0.6, right? And maybe it's moving a little bit at 0.8, but if I go out a little bit further, now 0.8 doesn't seem to be moving. The function value doesn't seem to be moving a lot there. So, but like at 1, it's still moving a lot, right? And it seems like it's getting settled as we get closer and closer to x is equal to 1, but it's never really getting settled at 1, okay? Now, if I compare this, let's look at that other function, right, we had expressed earlier. So here's 1 over 1 plus x squared. So that's going to be this function here in sort of the light green color. So, right, what I'll notice is this darker green color, as I increase these values, it seems to be getting close to that function. And if you look, like, as my m gets larger and larger, it's like it's becoming a better and better approximation as we get close to 1, but it's never a really good approximation at 1. Now, of course, that makes sense, because when I plug in x is equal to 1 here, this infinite series diverges. Why? Well, look at the sequence of partial sums. The first partial sum is 1. The second partial sum, so that's the sum of the first two terms, is minus 1. The third partial sum is 1 minus 2 plus 3. That gives me 2. If I keep going in this way, so the fourth partial sum will be negative 2. 3, negative 3, 4, negative 4, so on and so on. So what we see is that this sequence of partial sums doesn't converge, it diverges, right? In fact, it has these sort of alternating, it's alternating in sign, and the magnitudes are getting larger and larger and larger, right? So clearly when x is equal to 1, this thing is never going to sort of calm down, right? Because this series diverges at 1, okay? Now, the interesting question here, and an interesting question that we'll ask moving forward, is for what set of x values is this converging? Now, this is a question you actually answered probably back in a Calculus 2 course when you looked at something called Taylor series, right? So this is, in fact, an example of a Taylor series. And one of the things you do with a Taylor series often is compute its radius of convergence. Now, there's going to be much more interesting theoretical things we're going to want to look at. For example, even if I know for what x values this converges, how do I know that it actually converges to this function, right? This is a particular function. I can construct this series based off some properties, but how do I know that those two function that this series of functions is going to converge to this fixed function over here? I need some conditions on my function in order to make that true, and we want to understand what are those criteria. So that will conclude this video. Again, this has just been to give you an introduction to the idea of a sequence of functions and also to some extent a series of functions. And beginning in the next video, we will start to formally define some of these notions of convergence that we've been looking at and to try to prove properties of sequences of convergent functions. What we'll see is that while we can make a lot of use of properties we observed of convergent sequences of real numbers, there is something inherently different about sequences of functions that will warrant further exploration.